load cases and impact and stiffness and everything, or is it just sort of a waste of time? Could you just do the worst case scenario? And the answer is they actually do go through all the different cases. And some companies have more cases than others, but certainly Mercedes has more cases than Chrysler.
You should finish at 9:55.
Great.
Officially, the class is 5 minutes after, 5 minutes before, so the students can get to their class.
Okay, yeah, that's what we did last time.
And
Okay.
actually, what you're saying is true for big automobile companies. I've seen smaller things where they don't sell as many and they can't afford to do all those tests.
Right, that's true.
And if they get in trouble, it doesn't cost them $3 billion. But if a Mercedes or Chrysler doesn't do one of those tests and they have a problem, the recall can cost billions.
Yeah, so like a factory 5, they're in Massachusetts or somewhere, they won't do as many, that's true. But I guess in the mainstream automotive industry, they would do all. Okay, it's 9:05, why don't we get started here? Okay, so we're going to start off where we left off last time, and that's light weighting of a structure like a car body or a bicycle frame or a boat, could be a lot of things, an airplane, is a function of geometry and materials. I'm going to show you guys this every lecture, okay? Geometry and materials, because I think that's the main theme of this course, is that you can't really achieve light weighting or structural efficiency without looking at both geometry and both materials. You can't really get there. So that's one thing I definitely want you to take away. So having said that, we're going to start off this lecture with a story. So here are two basically useless cars. You're lucky if you can get one person in either of them. You can't get anything else in besides there. You can barely get a sandwich in these things. These are tiny little cars. They're basically for people who have a lot of money to play on racetracks. They're not very useful. In fact, what's even surprising is they don't even get good gas mileage. On the right, or on my right, is the Lotus Elise, okay, and on the left is the Renault Spider Sport. These cars came out at roughly the same time, about mid-90s, like I think it was 96 or 95. These cars have roughly very similar wheelbase, so the distance from center line to center line of the wheels, and basically really close to the same track. The Renault is a little bit bigger by a couple inches, but not dramatically so. They both have a tiny little 4-cylinder engine. The Renault is a 2-liter and the Elise is a 1.8-liter, pretty close to the same. Both these cars were somewhat revolutionary in that the primary load structure was made from aluminum extrusions. So you guys know what aluminum extrusion is? There's ways you can take like a billet of aluminum and you can jam it through a die and you can form a straight member with a uniform cross-section. They're very popular, like window frames and things use a lot. This is an extrusion right here. This aluminum piece right here on the board. You see a lot of them around. Anyway, now here's where the kicker is. The Lotus was about 1,600 pounds, and the Renault was a little over 2,000 pounds. Yet the cars were roughly the same size. So this kind of struck me as interesting. Back in the mid-90s when I was a graduate student, I used to obsess about this problem all the time about why was there 28% difference, 400 pounds or over 400 pounds difference in weight between these two vehicles. So even though the Renault isn't that much bigger, it still weighs 28% more. So why is that? It turned out the reason came down to how the extrusions in the body structure were joined. And Professor Egger is not going to like this because I'm going to talk badly about welds, and he's interested in welds. So the difference is that the Lotus chassis, as you can see in the upper right here, was glued together. The engineers at Lotus work with a company called Ciba-Geigy, which isn't around anymore. Rumor has it is that they used an epoxy, although I'm not sure that's true. I'm beginning to think it was an acrylic. And they took all these aluminum extrusions and they joined them together using adhesive, structural adhesive, similar to what would be used on an airplane at the time. On the other hand, the Renault although it was also made of aluminum extrusions, was welded together. The aluminum extrusions were all welded together to form the primary structure. And because of this welding, the Renault was a lot heavier. So what happened is whenever you weld a material, like a steel or an aluminum, you're some people have called it like casting in place. You heat this material up, it becomes molten, it flows, you put in maybe a filler material that's also hot and flows, and then it cools at some rate. That rate isn't real well controlled. What's driving the rate is all the material around it, heat transfer from that molten pool of liquid into the rest of the aluminum or steel around it. So it doesn't necessarily cool in a really controlled way. And you don't end up with a microstructure that is, shall we say, perfect. If you were to take a, if you were to plot, so here's two joints. This is just sort of like an overlap joint of, say, two tubes right here. So the Lotus had these glued tubes, or parts that were glued together. You can see the red glue up there in the picture. If you were to plot stress across this material, the strength of the material stays constant because it hasn't changed. Now, there was no welding, there was no heat cycle. The strength of the material is just as it was as it left the extrusion facility. However, when you weld two tubes together, you get weakening of the material that's in what's called the heat affected zone. So the area that got hot, when it cools, it doesn't really cool to the exact microstructure, maybe the optimal microstructure you wanted, and a lot of times it's softer than the material around it. Because of that difference in strength, the Renault engineers had to use much thicker wall thicknesses on those extrusions in order to get sufficient strength out of that joint. Okay, the Lotus engineers could go with a much thinner wall because they weren't going to lose anything. Now, unfortunately, with extrusions, as things are today, you can't really go to variable wall thickness. You're sort of stuck with one wall thickness. So because of that, the whole tube, the wall thickness of the whole tube, the whole structural member had to be dimensioned in order to compensate for that difference in strength. And that's why the car weighed 500 pounds more. Okay, so does everyone understand this? I'm pointing this example out because this example illustrates how materials can affect the structural efficiency of a primary structure on a vehicle, a car, an airplane, or whatever it might be. So today we're going to talk about the materials side of this equation. Okay, and this is the example just to illustrate, like I said. Hold on a second, Victor. This is just an illustration of this example of how materials really can affect weight. So.
Wouldn't the strength of the joint also be influenced by the shear strength of the adhesive? So, because if we're pulling on the example that you show here,
right.
Depending on the adhesive, we could have the adhesive be the failure point. And
this brings up a good point: is that the overlap of the joint is actually much larger than it would be if it was welded. And I've tried to illustrate that here, although I didn't mention it. And there is some weight savings that you lose because that joint you have to overlap a lot more material. But if it's good adhesive and it's well bonded, it'll fail in the adhesive rather than at the interface between the two, the aluminum and the adhesive. So they call this a cohesive failure versus a failure. So, but that's a good point. So there is some weight savings loss because you need more overlap in order to lower the stress in the adhesive enough so that the joint has sufficient strength.
I cover some of this in my welding course, but I agree with all of your analysis. The difference is this doesn't apply to steels.
Some steels.
You don't lose most steels because you don't lose the strength in the heat affected zone like you do on high strength aluminum alloys.
Mm-hmm.
The problem with the adhesive joint is even at $200 or $300 a pound, the adhesives may fail within 10 years.
A lot of airplanes are glued together.
That's right.
There's a lot of...
They use $400 a pound.
$400 a pound?
And they
Okay.
also do lots of prep of the surface of that aluminum to make sure it's a good joint.
Right.
Chrysler's a good example. They tried originally in 1985 to adhesively bond the door structure, and within 5 years the doors were falling apart.
That's Chrysler, though.
Well, that's true. But nonetheless, actually, that was on steel too.
Okay.
But anyway, we
Yeah.
could get into
We could get into this.
The principle you talked about is absolutely correct, but there are trade-offs.
Sure. There's a cost trade-off. The adhesive joints can be incredibly effective. The problem is it's really, really, really difficult to get a good adhesion, and I've experienced this firsthand. I once worked on a wind turbine that we're gluing together a bunch of aluminum with an acrylic adhesive, and the joints kept failing, and we didn't know why. We had a huge factory. It's about the size of 4 big grocery stores. It turned out some guy way in the corner was lubricating his jigsaw with a little bit of compound that had a little bit of silicone in it. That silicone somehow migrated over thousands and thousands of square feet, and it contaminated every joint in the factory. So we kept getting failed joints. So silicone is the killer of adhesive bonding. Remember that one. Right. So moving on here. So when you're interested in designing lightweight, efficient structures, the materials you need to design materials for, if anything, these two factors. So the yield strength per density or the stiffness, the Young's modulus per density. These are the parameters that are, these aren't the only parameters, but these are the ones I'm going to focus on for this lecture. Certainly there are other factors in making a lightweight effective structure, such as fracture toughness, energy absorption when it comes to cars for like a impact design, and then fatigue resistance. And there's a bunch more here, but I'm just going to, for the purpose of this lecture, we're just going to talk about these two, okay, just for simplicity. We're just going to focus on these guys. But so how do you design a material to do that? And how do you take some lump of metal and figure out a way to make it strong and stiff? Okay, you really can't do much with density for most materials. It kind of is what it is. You get aluminum, you get steel. In fact, in most materials, you really even can't do much about Young's modulus either. You're kind of stuck with what you got. There are some exceptions like lithium alloyed aluminum that you can decrease density or increase stiffness. You can increase this ratio, but for the most part, you're kind of stuck with E over rho. So really in this lecture, we're really just going to focus on yield strength density. Okay, so how do you do this? How many material science majors we got in the room again? Not that many, okay. So the material science majors this will be familiar, okay? The fundamental paradigm in material science for structural applications that I'm going to talk about is this here. It's the processing, structure, property, performance of a material. In some cases, maybe long ago, there were material scientists who went that way. So they had a material, they knew it was strong, they tested it, they didn't know why. They went through and they analyzed the properties that it had by measuring them. Then they cut up the material, they looked at the microstructure, they looked at the structure of the material and understand why it might be strong. And then they thought about, well, what processing did I do in order to get to this microstructure? More recently, I think material scientists have gone the other way up this guy, okay? And that is to understand, like, what processing would I need to do to get a certain structure that will give me certain strength, that will give me the performance I need. So as a mechanical engineering undergraduate, I was taught to look in tables, look in the back of your mechanics book and say, okay, aluminum's got a yield strength of 30 KSI. Okay, let's use that. Or I want to use this steel because it's got a yield strength of a gigapascal, whatever that might be. And then just use that and plug it into my finite element model. When I went to grad school, I got slapped on the wrist for thinking like that. So I went to grad school in material science, and they said, no, you're thinking all wrong, Don. You have to go the other direction. You have to say, what strength do I want? What fracture toughness do I want? And how do I then design a microstructure for the material or a mesostructure? And then what processing steps am I going to need in order to get there? Another way to think about this is what I'll refer to as the Olson diagram. I'm not sure it's officially called that, but I've been calling it this for 20 years. And the idea here is that you have a certain number of processes, some processes that lead to a material that's a final product. It might be a steel where you're solution treating, then you're quenching, and then you're tempering. It could be an aluminum where you're solution treating, quenching, and then artificially aging. Those processes lead to a certain microstructure, and then you can begin to make connections between the processes and those microstructures that you want to get. Okay, and then those microstructures can then lead to each of those microstructures will lead to a property that you want, and you can begin drawing the ties between them to understand what microstructure do I need in order to get a certain strength. Rarely, but sometimes you can say what would I have to do in order to get a certain stiffness, and that might be using a composite, for example. You can't really, we'll talk about this more later, but you can't really make a steel stiffer. A stainless steel is about the same Young's modulus of stiffness as a low carbon steel within a small percentage. A 7,000 series aluminum is about the same stiffness as a 6,000 series within a small amount. You can't really adjust that much. And then I just left a bottom box there open for some other property, which we're not going to define. We're just calling it a generic property. In designing the strength of a material, the topic of dislocations is one that always comes about. So if you look at a lattice of atoms and you calculate out the strength it would take to shear one, let's say, layer of atoms past another, okay, and then you compare that energy, and you can, in a way that's complicated, you can turn that into a strength for a bulk material or a bulk single crystal. You compare that to the strength of real materials, how strong real materials are in the real world. You'll you'll find out there's a huge discrepancy between the two. Okay? The reason that there's a discrepancy between what one would think from just going from first principles and calculating how much energy it takes to slide one plane of atoms over another is because of defects in the lattice. Okay, so defects can mean a lot of things. A defect could be a missing atom. It could be another atom that you don't want in there. A dislocation is a missing column of atoms. So if you apply a shear stress to this single crystal with this dislocation in it, with this missing column of atoms, as that dislocation moves from the stress, the material deforms in shear. Okay, and that really is the substance, the fundamental point of yield strength. What is it? How much energy does it take in order to get this material to start deforming via shear, or this crystal to deform via shear? And that has to do with moving this dislocation through the lattice. Okay, do you guys understand this? Missing column of atoms. Can't see it, it's too small. You can sort of see them in a TEM if you have a transmission electron microscope, if you use certain etching techniques. I've redrawn the top drawing in the bottom in sort of 3D because I wanted to show you that you can begin to think of a dislocation as a line. Okay, that line sometimes is called dislocation line. And then you can think about a bulk material where you start deforming this bulk material, and that line of dislocations, what causes the material to deform is that line of dislocations to move through the material. Okay, this is kind of abstract. You guys kind of get some idea what this is? Okay? Really important. This is the idea of dislocation motion, dislocation sliding. This is really the foundation of understanding how to increase strength. The idea is that you're trying to make it more difficult to move that line of dislocations through a material. And what can you do in order to stop it from moving? So, why isn't it going? Okay. So we just talked about this. That one. Okay, there we go. So, one thing you can do is these dislocation lines actually can move in various directions in different places in the material. And you can, when you take a piece of steel, for example, or a piece of aluminum, and you deform it, these dislocations will start to move all over the place as it deforms, and some of them will run into each other and tangle up. In some cases, you'll even generate more as you deform the material. You'll generate more dislocations. So more dislocations, more tangling among one another, increase in yield strength. As they get stuck and jumble up in one another, they can't move, and effectively the material increases in strength. In fact, the strength, this is one idea, one model on how this increases, but some material scientists argue that the strength increases with the square root of the dislocation density. So there's a lot of dislocations in a material. You'd be surprised. Like from what I've heard is that in a cubic centimeter of a piece of aluminum, there may be somewhere between 10 to the 5th and 10 to the 12th. That's a lot of dislocations in there. I've heard that if you added up the line, the length of line of these dislocations in like a little cubic centimeter of aluminum, that line can be as long as like 50,000 kilometers. So it gives you an idea of how small atoms really are compared to a cubic centimeter, and how many dislocations can be in there, adding up all that line, and how much really defect volume there is inside such a small little volume of material. So, for example, if I had a piece of aluminum or a piece of sheet of steel, and I stamp that sheet into a structure, say, for example, like a lid to a laptop, like Victor's here, for example. When you take that flat piece of aluminum, you stamp it into shape, you're effectively going up the stress-strain curve past yield. Okay, you're tangling up dislocations, creating more dislocations. Okay, now if you then take that part, unload it, maybe cut out a little section, you'll find out that little section that you cut out actually has a higher yield strength than the material did initially. And that is work hardening. That is strain hardening. That's again these dislocations that are kind of jumbled up in each other and can't move around. Any questions on this one? Okay, so this is a really simple idea of how you might increase the strength of a material with dislocations. Another one, it's called solution strengthening. So when you have a pure material like an aluminum, and you add say copper in there, you're alloying that material. Those copper atoms, or whatever it might be, maybe you're alloying with magnesium or manganese or a variety of different materials, silicone, all kinds of things go into a commercially available aluminum. those atoms have to go somewhere. And at sort of in the first analysis, when they're added fresh from the melt at the aluminum mill, those atoms either go one of two places. They either go to an existing lattice site, and they're called a substitutional element, okay, or they go to an interstitial site that's between the atoms. Typically, atoms, so let's call the alloy the solute, okay, and then the material, the base aluminum, is the solvent. Make sense? Solute, solvent. Solute's the alloying element, solvent's the mother material. If the solvent material, or say this, let me take that back. If the solute material, if the diameter of that atom, or let's call the lattice spacing, the distance between atoms, is within about 15% of the solvent atoms, then typically those atoms will go to a substitution position. Typically, for example, like a copper will go, because copper, magnesium, especially magnesium, will go to a lattice position. It's a substitutional alloy. Now, a material that's much smaller, like if you were to add a carbon or a boron or a nitrogen to aluminum, they're so small that they can't take up a lattice position. Instead, they take an interstitial position in between the atoms. Now, whether you're putting an atom at a lattice site or whether you're putting it at an interstitial site, it creates a distortion in the lattice structure. That distortion is enough to impede a dislocation from moving through the material. So that's a way to increase the material, increase the strength of the material. Kind of as a general rule, through substitution, you can increase the strength of a material by the shear modulus, okay, of the solute material divided by about 10. Okay, that's an increase in strength. And then for a interstitial material, you can increase the strength by about 3 times the shear modulus of the solute atoms. Okay, so from both of these you get a increase in strength, but from the interstitials you get a bigger increase in strength. Some other factors that affect the strength of a solid solution strengthened material are how much solute material you're putting in there. More solute gives you an increase in strength, as you can see from the bottom graph. Another thing that increases the strength is the valence state of the material that you're putting in there, the solute material, okay? If you have a large number of electrons per atom, the strength actually goes up even for a similar lattice spacing. And that you can see in the top graph. So this is, again, this is the same thing as before. You're just finding a way to stop dislocations or make it more difficult for dislocations to move through the lattice. That is effectively an increase in yield strength. Another tool is called precipitation hardening. Okay, so for example, with an aluminum, aluminums come from a mill. They take a bunch of aluminum and they take a bunch of alloying elements and they heat it all up. They mix it together, and then they cast out a slab. That slab will have what's called an alpha plus theta microstructure. So it's a dual phase material. That material that's comes straight from the mill. Okay, it comes straight from being solidified after being mixed together. Okay, what they'll do for like a 6000 series aluminum or a 7000 series aluminum, which these are kind of common aerospace alloys, they'll heat that material up to about 500 degrees Celsius until it forms a solid solution. So all those atoms that were in these little second phases in there, through the temperature, those second phases will break apart and they'll go into solution to form a solution strengthened alloy. In order to lock that in position, that material is then quenched. Okay, and now you've got a solid solution that's been quenched, and it is stronger than a pure material, so it's stronger there. But what some material scientists found out long ago is that material will actually begin to strengthen on its own. If you then take that material, put it in the corner and forget about it, come back in 2 weeks, it'll actually be stronger. And through looking at the structure, what they found out is that the atoms that were in those either interstitial or lattice positions kind of came back together later, right? And they formed what's called a little precipitate. Okay, it's a little second phase that's in there. They start off very small. They start off so small that you can't see them even at 1000x on an optical microscope. You really need a TEM to see them, or maybe a really good electron microscope. Okay, and then with time, these atoms, these little precipitates form with time. However, when you're building an airplane or a car, you don't have whatever month or 2 weeks in order to get your aluminum. You need it now. So they do what's called artificial aging. They take that material, that quenched material, and they put it in an oven at about 300 degrees Celsius for about, I don't know, 18 hours. And there's an ASTM spec you can look up on this as all the heat treats. And what they do is they force those precipitates to form much sooner than they would as if they just naturally aged. So initially, these precipitates are called coherent precipitates. Okay, so that means that if you look at the lattice structure of those precipitates, it matches up very closely with the lattice structure of the solvent material. So the atomic planes might line up really close, and they're coherent. They also typically have a higher shear modulus than the material around them, than the solvent, the aluminum. And these little coherent structures are very difficult for a dislocation to either penetrate and cut through or move around. When they're small and coherent, the dislocations cut through these precipitates, and it takes a lot of energy. And that's why it's very possible to get a very high increase in the strength of aluminum because it takes so much energy in order to get these dislocations to cut through these little precipitates. There becomes a time where the strength peaks. You get a fine distribution of many, many fine little coherent precipitates, and the strength of the material peaks. And hopefully when you get aluminum, when you buy your 6061 from, I don't know, McMaster Carr or down the street, whatever it is, the mill, the material is going to stay there. And the material is going to stay there during its whole life. And you can rely on that material to have that strength when it's reached its peak strength. The problem is that at some point, if you heat this material up again, if you heat it up over 150 degrees Celsius, for example, 150 degrees Celsius, those little precipitates will begin to grow again. They'll begin to go through a process called Ostwald ripening, where the little ones disappear and the bigger ones get bigger. And when they get bigger, they're not coherent anymore with the lattice around them. That's a big problem. At that point, it's very possible for these dislocations to actually kind of work their way around these particles and not have to cut them at all. And actually, the strength of the material begins to drop off, and you get a material that's less strong. So this is you can see I've put that in the bottom of the slide here. As you go, as the second graph here, or the third graph actually, as you go from right to left, you see that the precipitates grow, the coherency of these precipitates goes from being coherent to not being coherent, and then the dislocation moves through that material with a different mechanism. The mechanism in the middle is the preferred one. That's one that gives you the highest strength. So this is a real industrial problem. Let me give you an example. I once was a materials engineer at a company that was making let's call it a generator. Okay, so the generator had an aluminum housing. Okay, and there was a stator, so a group of wiring and some laminate steel material, silicon steel. Okay, that was assembled, wound up, assembled, glued together. And they had to find a way to get that structure. It's a stator for a generator. Okay, you guys know what a stator is? Stator and a rotor? Okay. They had to find a way to get that stator to stick in the housing of aluminum without turning. So it was stuck in there. They, as happens with a lot of engineering companies, they gave that part to a company to do. They outsourced everything to some company in Virginia, even though they were here in Boston. That company in Virginia decided to heat up that aluminum so that it expanded, and then they would drop the stator in and push it in. So they used the thermal expansion mismatch. So the stator wasn't heated at all, but the aluminum was. Aluminum expanded, stator went in. As far as they were concerned, there was no problem. When the aluminum cooled, it contracted on the stator. Okay, then the stator was unable to spin. It was stuck there. Okay, does anybody see a problem with this? Victor does.
Heating that will overage.
Exactly. So the company started having failures. The company I was working at started having failures. These aluminum housings were cracking, and they didn't know why. They went to their finite element analysis. They said, gee, we don't get it. The finite element cells, everything should be fine. This part has a factor of safety of 2. There's no way the stresses should be high enough for this aluminum to fail. But they were still getting cracks. Then they brought me and they said, Don, why the hell is this thing failing? And I said, I don't know. Let me call the manufacturer. So I actually took a trip to Virginia, and I found out that they were heating this aluminum at about 275 degrees Celsius. And even worse, they were putting it in an oven, and it was staying in this oven for an entire shift, up to 6 hours. So when we looked at this material under the microscope, we found that the precipitates had grown to the point where you could see them under optical microscopy. Okay? And when we did some indents, we found the material had lost about 65% of its strength. And that's why they were failing.
If you would just put it like below 150,
Depends on the alloy. So for a 6,000 series aluminum, you can often get away with that. For a 7,000 series aluminum, you could be in big trouble if you try that. If you're anywhere near 150C with a 7,000 series aluminum, you can get a very dramatic drop-off in strength, as I've personally measured. Okay, so you guys need to be aware about this. Whenever you spec out an aluminum part, if you work at a company, you're speccing out an aluminum part, and you know it's a part that's in a heat-treated condition, a 6,000 series aluminum, a 7,000 series aluminum, or 2,000 series aluminum, and you see that there's a post-process that's heating the material. It might be something like you're putting on a powder coat, and you're going to bake that powder coat on there. Always go in there and say, wait a second, this might not be right, guys. Okay, pull out your hardness tester and measure what the hardness was before and after, so you can confirm that it hadn't changed. And I've actually published material on this where I've taken a variety of different aluminum alloys and put them through a series of different sort of industrial relevant processes and then measured the change. So this is a real problem. Keep your eyes for this one. Do you have a question? No? Okay, I thought you raised your hand. All right. Okay, another strengthening mechanism is called the Hall-Petch relationship, the Hall-Petch strengthening. The Hall-Petch relationship says that the strength of a material is inversely proportional to the square root of the grain size. So that means that the smaller the grains are in a material, the stronger it's going to get, even to the point where the grains become nanocrystalline. So most metals have grain sizes sort of in the 10 to 100 micron range. In some cases, it's possible to shrink them, so they're much smaller than that, even like 5, 10, 20 nanometers. One of your professors here, Professor Chris Hsu, anyone know him? Professor Chris Hsu has started 2 companies based on this principle. One of them is called Ectalic, the other one's called Veloxant. And what these companies do is they make these microstructures that are nanocrystalline, and they've been able to realize extreme increases in strength from doing this. Now there is a problem with doing this that you guys need to be aware of, is that from my experience, back in the late 80s is when I saw material scientists starting to work on this. And I had a friend in grad school who found a way to make a nanocrystalline nickel. He took a piece of nickel, he melted it, and he vaporized it, okay, using high pressure gas. Then he solidified those little nickel particles on a cold finger, like a piece of chilled copper, okay? And Brian was able to take off this little ingot that he had made. He stuck it in a X-ray machine. He was able to measure the grain size, confirmed it was nanocrystalline. Everything was great. He measured the hardness. It was monstrous, 3 times the hardness of normal nickel. That was on Monday. So on Friday, he went to go show his advisor, pulled the material out, did a hardness check, and my God, it was the same strength as normal nickel. What happened? He was really embarrassed. So what happens with nanocrystalline materials is that because there's so much grain boundaries, there's a lot of energy associated with these grain boundaries. And the material will begin to grow. The grains will begin to grow to reduce the overall energy of the system. When that happens, you lose the advantage of the nanocrystallinity. So that's a big problem. Then you sort of lose your advantage. Sinbar? Sahir. It was close, sorry.
What's the relationship between the grain boundaries and the dislocations? Are those dislocations or are the dislocations within the grains? This is the question, the theory about why does the Hall-Petch relationship work? I guess that's kind of the same question, right? Okay. So just so you know, this relationship, you can find probably 100 papers online that confirm that this is true. And I've actually done this personally with indenting to see that it actually really does work. And there's I think some difference of opinion out there about why it works. Some material scientists would have you believe that the issue is that it takes a lot of energy in order for a dislocation that's in a grain to either sort of jump the grain boundary or at least push the shear that it's deforming by into the next grain boundary. That there's energy associated with moving that shear deformation over a grain boundary. And that increase in energy is what gives you an increase in yield strength. That's one theory. The other theory just says that you have a bunch of grains, there's going to be so many dislocations in a grain, if you can make them smaller effectively, you just increase the dislocation density. So if you increase the dislocation density, you're increasing the B there, right? So that's the same thing as increasing the strength. Some people would have you believe, and I'm not saying I disagree, but some scientists have proven that dislocation density really is inversely proportional to grain size. So smaller grains, more dislocations, higher strength. Does that answer the question? Okay.
I mean, I guess what I was kind of wondering is whether the grain boundary was a dislocation or whether the dislocation within the grain that's stuff there. Dislocation.
Yeah, I guess I don't have an answer for that. It's a good question. I think there are probably some people would argue that a grain boundary is a dislocation. I'm not sure if I agree, but we can talk about that. So as far as this instability with temperature, what Professor Shu here has been able to do is he's actually been able to coat these grains. He calls them painting the grains with another material. Okay, and that second material is actually thermodynamically stable, more stable than the bulk of the grain. So consequently, he's able to keep these materials nanocrystalline, at room temperature at least, indefinitely nanocrystalline. But even at elevated temperatures, where the energy is higher and there's more driving force to reduce grain boundary area, he's still able to keep them nanocrystalline over the long term. And that's a pretty amazing accomplishment. Another way to strengthen materials, which is actually very closely related, at least in the case of steel, is transformation strengthening. So with steel, like I've mentioned a couple times, you take a steel, and a lot of times if you want to strengthen, let's say like a eutectic steel or a hypereutectic steel, or maybe a hypoeutectic steel with a lot of carbon, but not past 0.77. You can take these materials and you can heat them up. They turn to austenite. Then you can quench them. When you quench them, some of the microstructure will turn to what's called martensite. So on the right here, on my right, is what you might have before you solution treated or austenized the material, which is a microstructure of ferrite and pearlite, where pearlite is ferrite and cementite, also known as iron carbide. Then when you heat this material up, again, it turns to austenite. And then when you quench it, it turns to martensite. The martensite, as you can see from this micrograph here, or these micrographs, is a much finer microstructure. The martensite is made up of these tiny little nanoscopic little platelets that kind of stick together. That's very similar in concept to having smaller grains. And that's why martensite is so much stronger than let's say, a ferrite material. The martensite is much more capable of tangling up and trapping dislocations because of its microstructure than was the ferrite. So here's a case where you've changed the structure of the material to form something that is stronger than what you started with. This is transformation toughening. And there's all kinds of literature on what's called a TTT diagram, so time, temperature, transformation. So this is what temperature you have to heat to, how quickly do you have to cool it, can you hold it somewhere, what do you have to do in order with a given alloy system to get to the microstructure that you're looking for in order to strengthen it. How can you design that material? Any questions on this one? Nope? Okay. Okay, the final strengthening mechanism I'm going to talk about is forming a composite. So you guys have probably heard of carbon fiber. You've probably seen carbon fiber bicycles, skis, tennis rackets, right? Carbon fiber, forming a composite where you have two different phases that are artificially put together by humans, by man, is one of the few ways you can actually increase the stiffness to density ratio of the material. So up until now, the 4 different strengthening mechanisms I showed you were all about changing the strength to density ratio. Okay? There are some exceptions, but just 30,000 foot view, primarily this is really the only way to increase the stiffness per density ratio. Like I said, there are exceptions. For example, like aluminum lithium, I believe I think you change the modules a little bit and then you also decrease the density when you put in like 6-8% lithium in aluminum. And you know, there are airplanes out there, especially in the military, that use this aluminum lithium alloy. But forgetting about that, the strength and stiffness of a composite material, again, where you're having a matrix material with, say, a fiber running through it, is governed by this law of mixtures, which says that you're going to put some combination of the strength of the reinforcement phase, like the fiber, and the strength of the matrix phase, like the polymer or the aluminum or whatever it is, and you're going to, that is related to the amount of material you put in will give you an enhanced strength, and it can also give you an enhanced stiffness. Some of the, just so you know, I mean, you've heard of carbon fiber, you've heard of fiberglass, I'm sure. There are also what's called metal matrix composites, where you put in a fiber that is more compatible with the metal. So I've once worked on a project where we put aluminum oxide fibers into aluminum. So the fibers were called Nextel fibers. They're incredibly stiff. You put them in aluminum and you can increase the stiffness by at least a factor of 2. And we did some experiments at Chrysler where we made brake calipers using this method. It didn't go into production, but it worked. So another advantage of composite materials is that you put the mechanical capability only where you need it. It's an orthotropic material. It means it has different properties in one direction than the other. So the properties normal to one another are different. This is very important. A lot of times if you have a part and you know it's only loaded, say, uniaxially, okay, right? If you made this part out of a metal, you have the same mechanical capability this way and that way. And there's weight, there's mass associated with having those properties in both directions. But if you don't use the strength in the transverse direction, then that's wasted weight. You're not getting anything from it. A composite is very different in that you can tailor the properties so that you're only putting the mechanical capability and therefore the extra weight, the extra density, only where you need it. And that's one of the reasons that carbon fiber, fiberglass can be very effective at making strong, lightweight structures. So that's the argument of orthotropic versus isotropic. Okay, we're gonna go back to this one here. Okay, so I showed you a generic version of this before. This is what I call an Olsen diagram, and this is a frame, a reference frame that an engineer, a material scientist can use to design a material to get certain properties. So let's use steel again. So let's say we start off with a steel that's from the mill. We've got iron ore, we've got some carbon, we've got some alloying elements. We put this in a blast furnace, we mix it up, we cast out ingots. Okay, that ingot can then be worked to increase the dislocation density. Cold working does that more effectively, but hot working can do it too. You can then maybe cut that billet up into little pieces and make it into some object like a door handle, a crankshaft, a bicycle crank, something. Okay, and then you can heat treat that one. In the case of steel, you would heat that up to a temperature again where you would transform all the ferrite and pearlite into austenite, and then you would quench that. During the quenching process, there's not enough time for that material to turn back into ferrite again, so it turns into what's called martensite. Martensite is stronger than ferrite. Sometimes martensite is too brittle for an application, so you do what's called a tempering step, where you use precipitation hardening to increase the toughness of the material. Okay, so those are the processes that you might use in order to make a steel component. Okay, you then know that these different processes produce different things in the microstructure. Okay, those things are listed here. For example, lath martensite. We talked about quenching and how that forms martensite. We've designed that. We've engineered this. We've said we want to get martensite, so we're going to do this quenching operation. We know that martensite leads to a high strength. But then we look at this material and we say, this isn't tough enough. How do we design this alloy so that it's tougher? And that's where the precipitation hardening comes in. So we talked about precipitation hardening, right? Precipitation hardening can be in a way to increase the toughness of the material. So then you know that you're going to put some alloying elements in there that are going to form some favorable precipitates. You've designed this. You've said we're going to put this material in here because we know that during a post-quench tempering step, that material, if we can precipitate out these called M2C carbides, so some metal plus a carbon, okay, we know that if we have this dispersion in there of these precipitates, the material will become tougher. So we just designed toughness in. Suppose we're looking for even higher increase in strength. We want little grains, like we talked about, right? We talked about putting little grains in the material because that gives you a higher strength from the Hall-Petch relationship. How do you do that? It turns out that niobium in steel is a very, very effective grain refiner. I've seen this in action a couple times working on structural steels for wind turbine towers. By putting niobium in, you can very effectively increase strength. You can reduce the grain size from in my experience, from like maybe 100 microns down to 10 microns. And that increases the strength while also increasing toughness. So again, you've designed in a secondary strengthening mechanism. You've reduced the grain size for whatever's left, whatever didn't turn to martensite. For example, it's austenite. And then there's another topic. So you can design the alloy so that when you quench it, you retain some of that austenite. It doesn't all transform to martensite. Some of it stays austenite. Now that's important because during the transformation from austenite to martensite, there's actually a volume change. Okay, without getting into too much deep stuff here, if you have a microstructure, and you've got, suppose all this is martensite, okay, and you've got a couple of grains of austenite in here, okay, and then this is martensite. Okay, as a crack, if this material gets a crack, and suppose it's being loaded like this, okay, so you're stretching open this piece of material. As this crack propagates through this martensite, because the martensite is so brittle, because there's so little possibility for dislocation motion, because the grains are so small and it's so good at tying up dislocations, the material can be kind of brittle. However, if it propagates to the point where it hits an austenite grain or chunk, piece of material, the energy associated with that crack opening up the material will actually can actually transform that piece of austenite into martensite. There's a volume change associated with that. That volume change can very effectively put a clamping load on the front of the crack, which is increasing toughness. The toughness of a material is the ability of a material to not propagate a crack when there's, to arrest a crack from propagating that already has a crack in it. That's toughness. That's different than energy absorption. But, and then there's other things. There's other things here, hydrogen resistance, fatigue. But I've given you some examples of how you actually design a material to give you these strength properties you want so that the final part has some performance that you're going to be happy with. It's going to last a long time. It's not going to break. The plane's not going to fall out of the sky. Your car is going to absorb enough energy when you hit something. This is what we call designing materials. Okay? Do you guys understand that? Because this is really important. When I was a mechanical engineer and I first, like I said, got into material science as a graduate student, I was really kind of fascinated by this, that you didn't have to just look at the table values in a book. You could say, well, what do I really need? What do I really want? And then go back and design the material to give you what you wanted. So one of your more recently joined professors is Greg Olson. He just started here, I think, in January, right? And Professor Olson actually, I think, is he's really like patient one when it comes to design and materials. He really, I think, has done more than anyone I've ever heard of to further the concept of designing materials. He taught a variety of different design and materials courses at Northwestern when I was a student there. He got his PhD here at MIT. He was an associate researcher here for quite a while, and then he got a full professor position or a tenure-track professor position at Northwestern. And he was there for a really long time. And during the time that he was at Northwestern, he started a company called Questech, which then uses these design of materials concepts to build new material alloy systems, basically from first principles. He's developed, along with some very interesting companies, all kinds of models for predicting what phases will form at different temperatures. Like I showed you that TTT diagram. Like these are programs, these are thermochemical programs that will predict these different phases and when they should form. And that can be very useful when designing a steel or an aluminum or beryllium or whatever it is, titanium, an Inconel. And then he's designed materials to predict, what grain size we're going to get, how long is it going to take, how long does our heat treatment need to be in order to get the right precipitations we want, and very interesting stuff. He's now a professor here. The reason I'm giving you this information is if you're more interested in this topic, he's got a lot of great papers on his website you can look up, and you can read if you're interested to learn more about this. And as I go through these lectures, I'm going to give you some other names of people who've written papers, kind of foundation papers on these interesting topics. And if you want to learn more about these things, I encourage you to go to the library upstairs in Baker and pull up these papers and read them, because you'll be amazed at the interesting things you can learn from these papers. With that, I'll say thanks for listening today, and any questions? Okay. Thank you guys. See you next.